Hi everyone, I'm Colin McIntosh and I'm a software engineer working on network automation and tooling at Netflix. For a few years now, we've all heard about the great things that streaming telemetry can offer. But if you've ever tried to use streaming telemetry, you may have found that there aren't many resources available to get started. Today, I'm going to be talking about a new piece of software in the network automation ecosystem, which is used at Netflix to stream state and configuration telemetry from network devices. It's called gnmi Gateway. But before I dive into the details of gnmi Gateway, I want to give everyone some background on streaming telemetry and gnmi. gnmi is the Google Network Management Interface, which is an open source protocol that is used to stream state and configuration to and from gnmi targets. In this case, gnmi targets are network devices. gnmi provides 4 RPC mechanisms, which are subscribe, get, set, and capabilities. Subscribe is the RPC, which we primarily use, where our network tooling sends a subscribe request to our network devices and in return receives a stream of updates about the state of the device. Get and set provide the functionality that you would expect, getting and setting specific pieces of data, and capabilities describes the services and data models supported by the target device. gnmi is defined as a specification and a protobuf model, both of which are available on GitHub, and I've linked out to them here from my slides as well. While gnmi is used to stream the data to and from targets, the data itself is structured using OpenConfig data models. OpenConfig is a working group of operators and vendors that have defined a set of data models that describe the state and configuration of network devices. These models are defined in Yang, which is a data modeling language defined by the IETF in RFC 6020. And these models are organized into a tree of various leaves. Here, I've included a small excerpt of the OpenConfig tree and what some of those leaves may look like. Note, this is only a small portion of the tree. It's actually much larger than this. At Netflix, gnmi is the protocol for streaming telemetry that we have chosen to focus on and feel best suits our needs. But there are others too. You may also be familiar with netconf, which provides some support for streaming telemetry. Or you may be familiar with sflow, which is another streaming telemetry protocol that streams flow data from routers. Or even syslog, which uses a similar push-based mechanism. This is a contrast to more traditional polling telemetry systems, such as SNMP, screen scraping, or proprietary vendor APIs that many network operators use today. Additionally, we use OpenConfig data models at Netflix and encourage our vendors to do the same. But there are other models available as well, such as IETF models or proprietary models that are specific to a single vendor. This diagram gives you a picture of how all of these pieces fit together. At the bottom is a normal gRPC connection that runs over HTTP2 and TLS. The gRPC code is auto-generated from the gnmi protobuf model, and gnmi carries data that is modeled in OpenConfig and has some encoding. When we talk about streaming telemetry at Netflix, we're typically talking about all of the components in this stack. So going back about 2 years at Netflix, like many here, we heard about all of the great things that streaming telemetry can offer. We saw it as an excellent option for managing our network with progressively more structured data and more real-time data. As we began to investigate streaming telemetry, we found that OpenConfig and gnmi provided the functionality that we were looking for. But at the time, we found that there were few existing systems and they were somewhat limited in their offerings. Most of the services that we investigated lacked support for many dynamic connections to our ever-evolving network, and some only supported a single connection to a single device. None of the services that we investigated provided high availability or failover for gnmi connections, and many of the services only focused on the subscribe RPC with no plans to add support for get, set, or capabilities in the future. What we did find was an extensive collection of reference work for gnmi on the OpenConfig GitHub. But while there were lots of individual components, there was really no robust system that was production ready for us. So following this survey of existing systems, we came to the conclusion that none of them fit our needs, and we decided to build our own. With this new system, we wanted a service that would provide highly available gnmi streams to consumers with clustering. As I mentioned, our network is ever evolving, and so is our network automation and tooling. To accommodate this, we wanted to allow for dynamic target loading so that GNMI targets and consumers are able to come and go without needing to redeploy or reconfigure the service. Much of our existing infrastructure is GNMI unaware today, so we also needed to be able to export our streaming telemetry data to non-GNMI services, such as our time series database or our big data platform. We also wanted to reuse as much of the existing reference work as possible, and we wanted to plan to support all of the RPCs that are provided by GNMI, as well as future extensibility. Lastly, we wanted to help the community ease their way into GNMI and streaming telemetry by providing a way to get up and running without needing to write any code. To that end, we built a service at Netflix called GNMI Gateway, and we've recently open sourced it as a contribution to the Open Config working group. And we hope that in doing so, we can help to enable easier adoption of GNMI. While you couldn't before run a single tool to integrate GNMI into all of your existing network automation, now you can. While we also understand that not everyone builds their tooling infrastructure the same as us, so we wanted to provide further flexibility by enabling a few different deployment scenarios. To start out with the simplest deployment scenario, we have just a single instance of GNMI Gateway with no clustering enabled. This is useful for testing the service out or for situations where high availability just isn't required. Here, we have a single instance of GNMI Gateway that uses a target loader to pull in a list of targets to connect to. GNMI Gateway will make all of the connections to the GNMI targets that are on the left-hand side of this diagram. On the right-hand side, GNMI Gateway serves a GNMI subscribe interface that other GNMI clients can connect to. GNMI clients, for example, may be tools with native GNMI support, or it could be network operators running GNMI from a CLI on their laptop. Also on the right-hand side, we have GNMI Gateway forwarding data to non-GNMI services via exporters. This second deployment scenario is the more typical scenario where you require clustering and high availability. Here, there are multiple GNMI Gateway instances that are all coordinating target connections amongst themselves, as well as replicating GNMI data to each other. In this diagram, the GNMI clients on the right-hand side make connections through an NLB, or a network load balancer, that will distribute client connections amongst the cluster instances. This NLB could be a layer 4 load balancer, such as we use, a layer 7 load balancer, or anything else that fits your needs, such as DNS load balancing. In a practical deployment, the GNMI Gateway instances in this diagram could be Docker containers, cloud instances, or servers in a data center, whichever is most appropriate for your situation. So going back to a scenario without clustering, you also have the ability to detach the exporter components from GNMI Gateway and run them on a separate server. We find this useful in situations where an exporter is performing a non-trivial workload that requires dedicated resources, or where we want to separate GNMI Gateway and an exporter for fine deployment control. In this case, the exporter on the right-hand side forms a GNMI connection into the GNMI Gateway instance on the left to subscribe to the telemetry stream. The exporter then forwards that data to the non-GNMI services. Other GNMI clients can still form connections to the GNMI Gateway instance on the left as well. In this fourth and final deployment scenario, we expand on the last deployment, but now with clustering. Here, we have a cluster of GNMI Gateway instances on the left that form connections to GNMI targets. And on the right-hand side, there are one or more exporter clusters that form their upstream connections through an NLB. This scenario is a very close model for what our real-world deployment at Netflix looks like for GNMI Gateway. To enable these clustering features in GNMI Gateway, we chose to integrate with Apache Zookeeper for coordination and leader election. Apache Zookeeper is a distributed configuration service that provides strong consistency and service synchronization. We chose Zookeeper because the service was familiar to us and provided all of the features that we required. If you're unfamiliar with Apache Zookeeper, please be sure to check out the GNMI Gateway README on GitHub, which includes some further details, as well as a command to get started with a development instance of Zookeeper. GNMI Gateway does provide an interface to extend all of these clustering capabilities to other services. For example, there have been some discussions about adding support for etcd, which we may consider in the future. But you're also welcome to add your own clustering services as well. I won't go over everything in this diagram, but this is a short overview of how the clustering works within the connection manager thread. Target connection metadata is received from a target loader, which is in the upper right-hand corner, and that starts the process of GNMI gateway acquiring the lock for a target. Once a lock is acquired, a connection to a GNMI target is formed and messages are forwarded to the GNMI cache in memory. Additionally, connections are formed to other GNMI gateway instances to facilitate the replication of received telemetry. So in order to form these connections to the GNMI targets, we require metadata about the target, such as its address, credentials, TLS certificates, etc. Target loaders are a plugin component that allows GNMI gateway to load this required metadata for each target connection. For example, target loaders can watch an NMS such as Netbox for devices with a specific tag. Or a target loader could form connections to other automation services that expose a GNMI subscribe interface, such as an SNMP poller. To get you started, we've included a few target loaders that can be used directly from the command line if you don't want to build your own. But if you do want to build your own, there is a Golang interface pictured here that you can extend fairly easily. The target loaders that we've included so far are for a watch text file as well as Netbox, like I mentioned. This diagram shows the inner workings of the target loader thread, which is the input to the clustering thread that you just saw. Here, the target loader collects the necessary data for each connection and then forwards new connections to the connection manager thread that you saw in the previous diagram. On the other side of GNMI gateway, we have exporters which forward data to non-GNMI services. For example, exporters can forward data to your NMS to keep collected state up to date or forward metrics to a time series database. As with target loaders, we've included a few exporters to help get you started from the command line, such as Prometheus, Atlas, and Kafka. But like target loaders, exporters are extendable as well with a simple Golang interface. And this is just a quick example of some of the data that you might see in another system as it was collected with GNMI gateway. Here we have a graph of a port channel's transmitted bits per second over time in Prometheus. And this diagram shows the flow of messages from the GNMI cache to the subscribe server and exporters. This is a fairly straightforward process, so I won't go over it here, but I did include it for reference. In addition to all the benefits that come with clustering, target loaders, and exporters, we've included a few extras to help ease the deployment of GNMI gateway, such as a Docker file for easy testing and deployment. We've also included some examples in the GitHub repo for various GNMI gateway configurations, as well as how to get started with GNMI gateway and Prometheus. We've also included the design documentations and diagrams in the GitHub repo that we used while building GNMI gateway for others to reference. So while we're very happy with how far we've come with GNMI gateway, we still have a lot of work planned. While we plan support for all 4 GNMI RPCs, we currently only use the subscribe RPC, so building out functionality for the set RPC is up next. We also want to develop additional exporters to help drive the integration of GNMI into more traditional automation tools and infrastructure. Finally, docs and examples can always be improved, and that's something that we want to add more of. We hope to soon have more configuration examples, as well as a more extensive deployment guide that goes beyond what's currently available in the README. To help you get up and running, here's a quick demo of GNMI gateway being started along with Prometheus that I hope you find useful. Here, I'm going to show you how to get started with GNMI gateway in Prometheus. First thing you'll want to do is head over to GitHub and grab the URL to git clone the repo. You'll need to have Git installed for this. You can change directory into the GNMI gateway folder. Here, we have an examples directory that contains a GNMI Prometheus example. Within there, there is a README that contains instructions on how to get started. The first thing you'll want to do is copy the targets-example.json file into the example directory and modify it to match the details of your network router. Let's do that now. You'll want to name the file targets.json so that way you don't have to modify the Docker file to get started. Go ahead and open that file for editing. So at the top, you'll notice that we have one request here named default. This request contains a single subscription for the path interfaces. This will return all of the data that is contained under the interfaces portion of the tree on our router. If you move down to the bottom of the file, you can begin to configure your target. The first thing you'll want to do is give the target a unique name. Next, you'll want to put in the address of the router. Along with the port that gnmi runs on. Next, you'll need to supply the credentials for the router. Be sure to keep your password secret. Next, you'll see that we have a request listed as default. If we head back up to the top, you'll notice that that is the name of the first request. This example assumes that your router does not have TLS enabled. If it does have TLS, you'll need to remove this no TLS field as well as add TLS certificates into the Docker file. We won't be covering that in this demo. Let's go ahead and save that file. Next, we'll want to grab the commands that we need to run. First thing we want to do is build the Docker container. We do include the Docker file with the example. In order to build it, you need to be at the root of the gnmi gateway directory, as Docker imposes restrictions that prevent you from building from within the examples directory. You can run the command from the README now. Next, we'll want to create a network that will allow two Docker containers to communicate with each other. We'll be setting up two Docker containers next. One runs gnmi gateway, and the other one runs Prometheus. Let's create that network now. You can go ahead and start the first container. This command will start our gnmi gateway instance, and it will point it at that targets.json file in our examples directory. Additionally, this will expose the port that the Prometheus exporter is running on. Here you can see that gnmi gateway has started without clustering enabled. We don't need clustering here because there's only a single instance of gnmi gateway running. You can see that it starts the connection manager as well as the gnmi server and the Prometheus exporter. Down below, you'll see that our target demo gnmi router connecting and subscribing, and then it connects. During this process, gnmi gateway begins to sync with the router and populate its initial cache with data. As you can see, after a few seconds, our demo gnmi router is synced. After the router is synced, gnmi gateway will only receive updates from the gnmi target. Can go ahead and open a new window. And we'll grab the last command to run. This command will go ahead and start Prometheus. You'll notice that we already supply the Prometheus config file, so you don't have to create one yourself. There we go, and now you can see that Prometheus is started. You can head on over to a web browser, and we can pull up the Prometheus web interface. If you go into the targets page under status, you can see that we have one endpoint for gnmi gateway, and it is up. The last scrape was 5 seconds ago, and the scrape took about 2 seconds. If we head over to the graph tab, you can see within the metrics list that all of our interfaces paths from OpenConfig and gnmi have begun to populate here. These are all of the automatically converted path names from the OpenConfig tree. We can select interfaces, interface, state, counters, out octets in order to get the interface transmit bits per second. You can get the rate over 1 minute. And we can multiply that by 8 because we want bits and not octets. So if we run that, you'll see that we begin to get values out. If we head on over to the graph, you can see data beginning to populate here. If we run this, you'll see that data is slowly beginning to filter in. If we let this run for a while, you'll see that data will continue to populate. Down below, you'll see a list of all of the interfaces that are being graphed currently. If we want to select just one of them, we can do that too. And there we go. We have the graph for a single port channel interface. And that's it. That's all you need to get started with gnmi Gateway and Prometheus. That's all I have for today. I'm glad that I was able to share this information about streaming telemetry and gnmi with you. As you've seen, it's easy to get up and running with gnmi, and I encourage you to go try it on your network too. Here's the URL for the code on GitHub. Please do check it out. If anyone has any questions or feedback after today, please feel free to shoot me an email or open an issue on GitHub. We do have some time now for questions if there are any.
Excellent. Once again, my name is Michael Voidy. I'm with the program committee, and I have the pleasure of having Colin McIntosh from Netflix here with us. There are 2 questions posted. Go ahead, Colin.
Hi there. So it looks like we have 2 questions so far. The first one from Rita is, can I talk about the scaling numbers for gnmi Gateway? So to give you an idea of what our deployment of gnmi Gateway looks like at Netflix, we have about a few hundred devices running on our we have a few hundred devices running in our deployment of gnmi Gateway. We have typically 3 instances running in a single cluster, handling those 100 devices. In our test deployment, we have a few 100 devices running on a single instance of gnmi Gateway. So we find that that really a single instance of gnmi Gateway can handle all of our devices. We haven't done any testing on the upper limit for gnmi Gateway, but that's definitely something that we want to do. Tony asked what OSs and vendors have we been able to use with GNMI Gateway. I will mention that one of the great benefits of GNMI is that it's based on a protobuf model that has code generated for lots of different programming languages, and it's therefore supported on lots of platforms. So really any implementation of GNMI should be supported with, any implementation of GNMI and OpenConfig should be supported by GNMI Gateway. We specifically have primarily used GNMI Gateway with our Arista devices. And we've done some testing with at least one Wi-Fi vendor who provides a cloud implementation of GNMI Gateway to allow us to access our devices. And we also have a few internal services that run GNMI Gateway as well. Or I'm sorry, that run the GNMI subscribe interface as well that we connect GNMI Gateway to, in addition to our network devices. Barry asks, are these examples for that clustering case, or are there some simpler ones? I'll need to rewatch it because it was going fast. So there are the 4 examples there. There's the first example was for a setup without clustering, so you don't need an instance of Zookeeper setup. So if you just want to go try out GNMI Gateway, you can basically do set up an instance the same as I just did in the demo, where you have a single instance running somewhere. So that tends to be pretty simple, and you can just run that as a single command. If you do want to start to scale up, you'll need an instance of Zookeeper, and basically you just point all of the GNMI Gateway instances of the same Zookeeper instance, and they will all begin to coordinate with each other. But there's also more details on that in the GNMI Gateway README. But also feel free to open an issue if you have any additional questions, or send me an email. Do you have an API that follows open API standards? So GNMI Gateway is GNMI in and GNMI out, which is based on protobuf. So I'm not super familiar with Open API, so I'm going to say no, but I can follow up on that if you want to shoot me an email, Travis. Oleg asks, Prometheus is a pulling system. How do you stream to one? So you're right, Prometheus actually is pulling, which is what the exporter is doing. So when GNMI Gateway starts up the Prometheus exporter, what's happening is the GNMI Gateway serves a Prometheus exporter web page that then Prometheus is pointed at the GNMI Gateway instance and scrapes. I will say that the Prometheus example is just something that I kind of added in to use as a proof of concept. We don't actually use Prometheus at Netflix, or at least within the network space. We primarily use a Netflix-built service called Atlas. But yeah, so Prometheus pulls the metrics from GNMI Gateway. And Oleg also asked, have we considered Telegraph InfluxDB combination? I think there's probably 2 questions there, or maybe there are. So one was, do we consider using Telegraph instead of GNMI Gateway? We did look at Telegraph and being able to send data to InfluxDB. One of the, I believe the Telegraph GNMI plugin was contributed by some folks at Cisco and uses the same GNMI library as GNMI Gateway. The issue with Telegraph was that there was no high availability, and it only supported basically like a static config file, and it found it difficult to basically like dynamically load our targets. And also it didn't really provide us an ability to serve a GNMI subscribe interface, so we could have various dynamic clients being able to connect and ask for data. So that was one reason why we didn't go with Telegraph. And then we also have considered making a GNMI Gateway exporter for InfluxDB. It's just not something that we've gotten around to. So hopefully we'll be able to connect GNMI Gateway to InfluxDB.
I think that's it. So yeah, if there are no more questions, thank you everyone for the time and for tuning in. Please feel free to shoot me an email, colin@netflix.com if there are any questions, or you can open an issue on GitHub, github.com/openconfig/gnmi gateway. Thanks everyone.
Thank you very much, Colin, on behalf of the program committee.